Welcome to today's webinar on analyzing the impact of parameterized eccentricity on Nissan Leaf performance. My name is Sumit Singh and I am an electric motor expert at EMWorks. EMWorks is a leading provider of electromagnetic simulation software for electrical and electronic designs. At EMWorks, we specialize in offering state-of-the-art electromagnetic simulation solutions that span a broad range of applications from DC to millimeter wave frequencies. Our software seamlessly integrates with popular CAD platforms like SolidWorks and Inventor, allowing engineers to simulate and analyze a wide array of electrical systems. Our product portfolio covers various areas, including electric motors, generators, transformers, power electronics, antennas, and wireless circuits, catering to both low and high frequency electromagnetic phenomena. To make this webinar interactive and engaging, I encourage you all to utilize the chat box option to ask questions throughout the presentation. We value your participations and we will address all of your queries and concerns during the dedicated Q&A session at the end. Here is today's agenda. We will explore the impact of eccentricity on the electromagnetic performance of electric motors. Next, we will delve into the causes of eccentricity and understand how this phenomena affects motor performance. Our case study focuses on an interior permanent magnet synchronous motor. The first part of our studies investigates static eccentricity. We will examine the impact of a fixed rotor displacement on the motor's torque, radial force, and flux density characteristics. Moving forward, we will explore dynamic eccentricity. This scenario involves continuous rotor displacement during motor operation. Our study also includes an investigation into mixed eccentricity. This scenario combines elements of both static and dynamic eccentricity. To illustrate our findings, we will provide a live software demonstration using the EMWorks 2D software. We will showcase how simulations can be conducted to evaluate and visualize the effects of eccentricity on the motor performance. This demonstration will help solidify our understanding of the concepts discussed. And finally, we will conclude our webinar by summarizing the key insights gained from the case studies. Once again, we will open the floor for a Q&A session, so please feel free to ask your questions you may have and we will address them to the best of our abilities. Eccentricity in a motor refers to the condition where the rotor deviates from its intended center line within the stator. This eccentricity can cause various issues in motor performance, such as increased vibrations, reduced efficiency, and increased wear on the motor components. There can be several causes of eccentricity in a motor, including: first, the manufacturing defects. Eccentricity can result from manufacturing errors such as misalignment of motor parts during assembly or inaccurate machining of rotor or stator components. These defects can lead to uneven air gaps between the rotor and stator, causing eccentricity. Second, we have mechanical stress. External mechanical forces or excessive mechanical stress on the motor, such as impacts, vibrations, or improper handling during installation, can cause the rotor to shift from its intended center line, hence resulting in eccentricity. Third, we have bearing wear. Worn out or damaged bearings can introduce eccentricity in a motor. Bearings are responsible for maintaining the precise alignment of the rotor within the stator. If the bearings degrade or fail, the rotor can become eccentric. Next, we have thermal effects. Temperature variations can cause the expansion or contraction of motor components, which may lead to changes in the rotor's position. If the expansion or contraction is uneven or not properly compensated, eccentricity can occur. Fifth, we have voltage imbalance. In three-phase motors, voltage imbalance between the phases can cause uneven magnetic forces, resulting in eccentricity. Imbalanced voltages can be caused by faulty power supply connections, unbalanced loads, or issues within the motor's internal connections. Sixth, we could have the rotor core faults. Damage or deformation in the rotor core, such as shorted laminations or broken rotor bars, can induce eccentricity. These faults disrupt the magnetic field and cause the rotor to deviate from its center line. And finally, we could have uneven air gap. The air gap between the rotor and stator should be uniform for proper motor operation. If the air gap is uneven due to improper installation, degradation, or mechanical damage, it can lead to eccentricity. So, detecting and correcting eccentricity early is crucial to prevent further damage to the motor. Regular motor maintenance, including vibration analysis, visual inspections, and electrical measurements, can help identify and rectify eccentricity issues in a timely manner. So let us see what are the different detection methods for eccentricity. First, we could have vibration analysis. It is a widely used method to detect eccentricity in motors. An accelerometer is typically attached to the motor or its housing to measure the vibration levels. Eccentricity causes uneven forces resulting in increased vibrations. Analyzing the vibration signatures can really help identify the presence and severity of eccentricity. Second, we have current analysis. Monitoring the motor's current can provide valuable insights into its condition. Eccentricity can lead to unbalanced magnetic forces, resulting in increased current fluctuations. Current analysis techniques such as motor current signature analysis (MCSA) can help detect eccentricity-related abnormalities in the motor's current waveform. And we can also have a thermal imaging. Thermal imaging or infrared thermography can be used to detect temperature variations in the motor. Usually, eccentricity can cause localized heating due to increased friction and magnetic losses. By capturing thermal images of the motor during its operation, areas with abnormal temperature patterns can be identified, indicating potential eccentricity. Next, we have air gap measurement. Eccentricity often results in uneven air gaps between the rotor and stator. Measuring the air gap using specialized equipment such as air gap sensors or feeler gauges can help identify variations in the air gap and indicate the presence of eccentricity. Another method could be stator core flux analysis. Stator core flux analysis involves analyzing the magnetic flux in the stator core of the motor. Eccentricity can cause changes in the flux pattern, and specialized instruments such as flux probes can be used to measure and analyze the flux density. Deviations from the expected flux distribution can also indicate eccentricity. And finally, we could have a visual inspection. A visual inspection of the motor can sometimes reveal physical signs of eccentricity, such as misalignment of rotor and stator, rotor rubbing against the stator, or abnormal wear patterns. Inspecting the motor for any visible anomalies or damages can provide initial indication of eccentricity. Moving ahead, let us look at the effects of eccentricity. First, it could have, of course, the increased vibrations. Eccentricity causes an imbalance in the rotor, which results in increased vibration during motor operation. These vibrations further can lead to a mechanical stress on the motor components, affecting the overall performance and potentially causing damage. We could also see the reduction in the efficiency. So eccentricity disrupts the normal alignment between the rotor and stator, resulting in increased friction and losses. This can reduce the motor's efficiency as more energy is wasted in overcoming the additional forces generated by the eccentricity. Next, we have the increased friction and losses due to eccentricity can cause motor to generate more heat. This can lead to elevated operating temperatures, which can further degrade the motor's performance and potentially shorten its lifespan. Eccentricity can result in uneven contact and rubbing between the rotor and stator. This can lead to increased wear on motor components such as bearing, rotor bars, and stator winding. Over time, this wear and tear can cause further deterioration of the motor's performance and reliability. Eccentricity can also cause uneven air gaps between the rotor and stator, and this will lead to unbalanced magnetic fields. This can result in torque fluctuations and reduced torque output, affecting the motor's overall performance and stability. Next, we have abnormal noise. The imbalanced magnetic forces and mechanical stress caused by eccentricity can produce abnormal noise during motor operation. Unusual or increased noise levels can indicate the presence of eccentricity and can be warning sign of potential motor issues. Finally, the combined effect of increased vibrations, heat generation, wear and tear, and reduced efficiency can lead to a shortened motor lifespan. If eccentricity is not detected and corrected in a timely manner, it can significantly impact the motor's overall durability and reliability. So, to analyze the effect of eccentricity on the electric motor design, we have three different products. First, we have Motor Wizard tool. It is a template-based motor design software that allows user to accurately solve both electric and magnetic problems. It includes electrostatic, magnetostatic, and transient solvers equipped with integrated analytical and finite element based solvers. Second, we have the EMWorks 2D tool. It is a 2D electromagnetic simulation software that uses finite elements to solve magnetic, electric, and transient problems. EMWorks 2D allows you to study the effects of the geometric or simulation parameters changes on the design. It also allows coupling a transient magnetic study to mechanical motion and thermal. And third, we have EMS tool. It enables users to do both electric and magnetic simulations using the complete 3D geometry. EMS is a true multiphysics software that enables users to couple the magnetic, electric design to circuit, motion, thermal, and structural analysis on the same model in a hassle-free integrated environment. So, we'll be using these tools to design and analyze an electric motor with the effect of eccentricity. So, the designer can set up the simulation scenario with the desired eccentricity type and magnitude. The simulation results provide the motor's electromagnetic behavior, including the flux density, magnetic field, torque, stator tooth forces, etc. So the first step is to create a study with eccentricity. To analyze the impact of eccentricity on a machine, the designer need to create a new study by clicking on the new study button in the EMWorks software, and in this study the designer can choose the type of eccentricity to be analyzed, either as static, dynamic, or mixed. If the designer chooses to analyze the impact of static eccentricity, they need to enter the shift in the rotor rotation axis and the angle based on the percentage of the air gap magnitude. The designer can do this by inputting the parameter in the software interface. If the designer chooses to analyze the impact of dynamic eccentricity, they need to enter the shift in the rotor motion based on the percentage of the air gap magnitude. The designer can input this parameter very easily using the software interface. And finally, if the designer chooses to analyze the impact of mixed eccentricity, they must enter the parameter used in the static and dynamic eccentricities. The designers can input this parameter in the same manner for the static as well as for the dynamic eccentricity. And then finally, once the study and parameters have been defined, the designers can run the simulation in EMWorks. The software will use the parameters entered by the designer to create a model of the PMSM machine with the selected eccentricity type. The simulation will then generate results for the designer to analyze and interpret. By following these steps, designer can use our software to analyze the impact of eccentricity on PMSM machines and make informed decision based on the simulation results. So let's begin with our design specification. Our configuration is 48 slot and 8 pole with the base speed of 750 rpm. It's an inert rotor position type motor having a stator outer diameter of 198 mm and with the stack height of 150 mm. We'll be giving excitation of 250 ampere and we have selected a ferrite type magnet with grade 8. Moving ahead, to begin the performance analysis in EMWorks 2D software, first different study settings are needed to be done, such as materials, boundary conditions, mesh and winding. Next, before moving into the different types of eccentricity analysis, let us understand what are these types. First, we have static eccentricity. Static eccentricity is characterized by a fixed displacement between the center of the rotor and the center of the stator, as you can see on the first animation. In other words, the rotor is off-center in a consistent manner. This type of eccentricity often occurs due to improper assembly or misalignment during motor manufacturing or installation. Static eccentricity can lead to uneven air gaps between the rotor and stator, again resulting in unbalanced magnetic forces and torque ripple. And you can see here the stator tooth, which is the closest to the rotor core, is highly saturated compared to its diametrically opposite stator tooth. Next, we have dynamic eccentricity. It involves a varying displacement between the rotor and stator centers as the motor rotates. The dynamic eccentricity may be caused by factors such as bearing wear, shaft deflection, or uneven magnetic pull. As the rotor eccentricity changes during rotation, it introduces periodic variations in the air gap, resulting in additional vibrations, noise, and potential performance issues. And finally, on the right hand side, we have the mixed eccentricity, which is a combination of static and dynamic eccentricity. In this case, there is a fixed offset between the rotor and stator centers and additionally variations during rotation. Mixed eccentricity can arise from a combination of factors such as misalignment during motor assembly and subsequent dynamic changes caused by operating conditions or mechanical wear. So let's begin with our first type of analysis, that is the static eccentricity. And here you can see the mesh images for the different conditions. First, we have a healthy model which represents a healthy rotor of a motor with 0% of eccentricity. Next, we have mesh for a static distance of 50%, which refers to a certain degree of eccentricity between the rotor and stator. And then we have a mesh for a static distance of 90%. Now, if we look at the results, when a permanent magnet motor experiences static eccentricity, where the rotor's geometric center deviates from the stator's geometric center, it can have a asymmetric effect on the magnetic field distribution. This asymmetricity affects the individual teeth of the stator differently, leading to variations in their magnetic characteristics. In particular, tooth 1 and tooth 25 are affected in opposite ways as the percentage of the static eccentricity increases. Now, if we look at the tooth 1, as the percentage of the static eccentricity increases, the magnetic field distribution in the air gap between the stator and rotor becomes asymmetric. In this case, tooth 1, which is closer to the eccentricity, experiences a decrease in the magnetic field strength. The reduced magnetic field in the vicinity of tooth 1 leads to a decrease in the magnetic force and consequently a decrease in the torque generated by tooth 1. This decrease in tooth 1's torque can be attributed to the reduced flux linkage and smaller effective air gap between the rotor and tooth 1 due to the eccentricity. Conversely, tooth 25, which is diametrically opposite to tooth 1, experiences an increase in the magnetic field strength as the eccentricity increases. The increased magnetic field near tooth 25 results in a higher magnetic force and consequently an increase in the torque generated by tooth 25th. This increase in torque 25th torque can again attribute to an enlarged effective air gap between the rotor and tooth 25 due to the eccentricity. The asymmetric effect on tooth 1 and tooth 25 is a result of the uneven distribution of the magnetic field caused by the static eccentricity. The magnetic field is stronger on one side of the air gap and weaker on the other side, leading to differential torque effects on the teeth. This uneven torque distribution can result in torque ripple and potentially affect overall motor performance. It is important to note that specific impact on tooth 1 and tooth 25 may vary depending on the motor design and magnitude of the static eccentricity. The mentioned effects are general tendencies observed in PMSMs experiencing static eccentricity. Next, we have when the eccentricity increases, the following effects are also observed. The first we can see is the increase in average electromagnetic torque. The average electromagnetic torque in a PMSM is generated due to the interaction between the stator's magnetic field and the rotor's permanent magnets. When the rotor is eccentric, the air gap between the stator and the rotor varies as the rotor rotates. This variation in the air gap leads to a non-uniform distribution of magnetic flux density in the air gap. Now, during the eccentric rotation, the magnetic flux density is higher in some regions and lower in others compared to a perfectly centered rotor. The regions with higher flux density contribute more to the overall torque generation. As a result, the average electromagnetic torque increases when the rotor is eccentric because more torque is produced by the regions with higher flux density. Next, we can also look at the second plot, which is on the right hand side, which shows the reduction in torque ripple. Torque ripple is a fluctuation in the output torque of the motor as it rotates. It is undesirable characteristics as it can cause mechanical vibrations and acoustic noise. Torque ripple is primarily caused by the interaction of multiple harmonics in the motor's magnetic field. When the rotor is perfectly centered, the magnetic field distribution is symmetric and the harmonics tends to cancel each other out to some extent, resulting in lower torque ripple. However, with an increase in rotor eccentricity, the magnetic field distribution becomes asymmetric. This can lead to better harmonic cancellation and reduced torque ripple. as you can see in the plot. Furthermore, a more significant air gap variation caused by eccentricity can smooth out torque ripples as the motor rotates. The torque contribution from different sections of the rotor will be more balanced, leading to a reduced overall torque ripple. It is important to note that while some level of eccentricity might help improve performance as described here, but excessive eccentricity can lead to other issues such as increased mechanical stress, increased wear, and reduced motor efficiency. Next, let us look at the flux density plot. This non-uniform air gap results in a variation in the magnetic flux density distribution within the air gap. In the regions where the air gap is smaller due to the eccentricity, as you can see in the case of 90% static distance, or the magnetic flux density tends to be higher. Conversely, in the regions where the air gap is larger, the magnetic flux density tends to be lower. This non-uniformity in the flux density distribution is a consequence of eccentricity. The average flux density refers to the average value of the magnetic flux densities across the entire air gap. Due to the non-uniformity caused by eccentricity, the average flux density decreases. Since the region where the lower flux density contributes to the overall average, it is important to maintain a uniform air gap in a PMSM to ensure proper and efficient motor operation. Eccentricity is generally considered an undesired condition as it can lead to various issues. Next, let us look at the effect of static eccentricity on the different angular position or location of the rotor with respect to the stator. Here we have few key angular positions such as at 0 degree, at 90 degree, at 180 degrees, and at 270 degree. Now if we look at the effect of these results on the radial forces based on different angular position. For tooth 1, it increases when it is close to tooth 1, but at the same time the radial forces are lowest for tooth 25, and then vice versa. So depending on the angular position, the forces remains the same as we saw, and the profile of the forces remains the same as we saw in the previous results. Moving ahead, now in the case of 50% dynamic distance, the flux density plot may show fluctuations in the magnetic field strength. And just a second, yes, and flux density values across the air gap as the rotor rotates. The plot might exhibit periodic changes in the flux density distribution with peak and throws occurring at different angular positions during each revolution. On the other hand, if we look at the 90% dynamic distance, indicates more significant displacement of the rotor's center from the stator's center during motor operation. The flux density plot for this scenario may exhibit more pronounced variations and larger deviation in the magnetic field strength across the air gap. Now if we look at the results, in the case of dynamic eccentricity, the peak tooth radial forces is the same on all the teeth, but occurs at different time instants during each rotation. When the rotor experiences dynamic eccentricity, the air gap between the rotor and stator continuously changes as the rotor rotates. This variation in the air gap leads to an uneven distribution of the magnetic field and consequently the magnetic forces acting on the stator teeth. During each revolution of the rotor, the maximum radial force acting on the stator teeth occurs when the eccentricity aligns with a particular stator tooth. At this point, the air gap is minimized, resulting in a stronger magnetic field and higher magnetic forces on the specific tooth. However, since the dynamic eccentricity is continuously changes, the relative position between the rotor and stator, the peak tooth radial forces occur at different time instances for each tooth throughout a complete rotation. This means that each tooth experiences the maximum radial force at different point in time during each revolution. Next, a similar behavior can be observed for dynamic eccentricity, for average electromagnetic torque, and torque ripple, as we discussed previously in static eccentricity. The average torque increases and the torque ripple reduces as the dynamic distance is increasing. Moving ahead, we'll look at the mixed eccentricity, which is nothing but the combination of static. As we can see here, we have a shift in the static component, as well as we have a dynamic component around which the motion will be generated for the rotor. And here we'll discuss two different scenarios where we'll maintain the static at 50% and will vary the dynamic from 10% to 40%. And another case where we'll fix the dynamic percentage at 50% and will vary the static shift from 10 to 40 in the steps of 10%. Both the case is analyzed at 0 degree static eccentricity angular position. So if we look at the results, we can see in overall the radial forces increases as the rotor approaches towards the stator core, and whether it's a mixed combination of static or dynamic, the behavior remains the same. So the forces computed on this tooth, the peak values are same whether we have a fixed number of static or dynamic eccentricity. Moving ahead, now we will quickly go through the demonstration of EMWorks 2D software and see how do we set up a study with eccentricity analysis. So EMWorks is a powerful electromagnetic simulation software with CAD integration. So our products are embedded inside this SolidWorks, which can be accessed through the tools, and you can find our product right away there. So in the first step, you have three options. Either you can sketch your design directly inside SolidWorks, or import a pre-existing design template from a motor wizard, which allows you to bring your motor geometry quickly and efficiently into this platform. Or the third option could be to import your design through any third-party CAD tool. So once your design is ready, it's time to create a study. So in this step, we'll click on the EMWorks 2D Manager if our geometry is in 2D, or we'll use EMS Manager if our geometry is 3D. So once the design of all the components are done, I'll be clicking on EMWorks 2D Manager. Once I'm inside the EMWorks 2D Manager, I'll right click on the model and create a study. Now under the new study section, I'll choose transient magnetic, where I'll define the time duration. Let's say the time period is 0.02 second, and I'll create the steps, so which I can keep it as, let's say, number of steps could be 100, so 0.02 divided by 100, and then I need to click on the coupling analysis. Here I can select the eccentricity. From there I can start setting up my eccentricity study. Here I can choose either static, either dynamic eccentricity, or the mixed eccentricity, which is a combination of both static as well as the dynamic parameter. So here I need to set the initial angle of my design, and then the speed of the rotor, then the air gap length, and with the help of this air gap length data, we will be able to shift the rotor automatically for our user based on the percentage of the static eccentricity as well as its angle and the dynamic eccentricity. Now it could be a scenario where the speed of the rotor could be spinning at different speed of its eccentricity. So here in case of dynamic eccentricity, we can also set the rotating speed. Once we have completed our study, we can click on the checkbox and our study will be created. So once the study is created, you can start setting up its material. EMWorks provide a comprehensive material library, as you can see on the right hand side of your screen, with a vast list of predefined materials, each accompanied by their respective properties. This library covers a wide range of commonly used materials, including metals, alloy, ceramics, and more. Whether you are simulating electrical machines, transformer, or any electromagnetic device, you will find the materials you need for accurate modeling. And we also understand that every project is unique and you may have a specific materials that are not included in the predefined library. So that's where EMWorks offer customization options. With our software, you have the flexibility to add new materials and define their properties according to your requirement. So once the material is assigned to all the components of your motor, the next step comes to create the boundary conditions such as the load restraints, and select the components that are responsible for the force or torque calculation, and for motor application it's mainly all the rotor components and the magnet and the rotor core. And then comes the teeth force calculation. So here we simply click on the tooth force, where we need to select one of the edge of the tooth. Let's say I'll select this one, and my design has 48 number of slots. So here I'll simply enter my parameter as 48 and click on the checkbox. The software will automatically detect all the edges of the tooth and will create a study, as you can see here. Next we have meshing capability that allows you to divide your geometry into smaller elements, enabling accurate calculation and simulation. So here you have a control over your mesh density, allowing you to adjust the element finer or coarser as needed using mesh controls. This feature enables you to balance computational efficiency and accuracy. So here you can see the mesh for our geometry. And finally comes to set up the excitation for our coils. Here you can simply create a windings for your phase A coil for go path, as well as phase A as a return path. You can simply choose the type of excitation that you're interested for the coils, either current driven or voltage driven, and choose this type of excitation, either sinusoidal, or you can also import your own custom current versus time curve. So once the winding setting is done, you can also click on the windings properties, and you can choose the number of turns, its wire diameter for the wires. So once the winding setting is done, the final step is to run the analysis. Here you can find the result in form of table properties and its filled plots. Under the table we have results such as flux linkage. You can simply click select all the flux linkage property for all the phases, add into your parameter, and click on the plot preview. You can also look at its torque, add into your plot, and then look at the torque. So here the average torque is around 80.5 Newton meter. You can easily click on the plot pop-up, where you can get the data of your plots, and here we can see the maximum and minimum, and can easily find the average of this torque. And then finally we have the tooth forces. Here I have selected the tooth 4 of the tooth from my study, and I can look at its radial as well as tangential forces. So I can select all of them, and this one is for the static eccentricity, and we can see here the tooth 25th, which is represented in a red curve, has a higher variation in the radial tooth forces compared to tooth 1, which is in the green color waveform, experiences a lower radial tooth force. We can also look at its field plot. We can simply create its magnetic flux density plot for it. So as we can see, this rotor is shifted by 50% at 0 degree, and In such a manner, we can analyze the effect of static eccentricity. Similarly, we can create a new study, or we can edit this study and analyze for the dynamic as well as for the mixed eccentricity. So going back to our presentation, in today's webinar, a simulation of a Nissan Leaf model was conducted using EMWorks 2D software. The purpose of the simulation was to perform a parameterization study focusing on different types of eccentricity inputs. In this study, the focus was on 3 types of eccentricity: static, dynamic, and mixed. The simulation aimed to evaluate the electromagnetic performance of the motor under current excitation, specifically analyzing 3 key parameters: torque, radial forces, and flux density. For each type of eccentricity, the software likely allowed researchers to input the relevant parameters and simulate the motor's behavior. The simulation would generate data and results comparing the electromagnetic performance for each type of eccentricity. By comparing the torque, radial force, and flux density under different eccentricity scenarios, the researchers or designer would gain insights into how each type of eccentricity affects the motor's performance. This information can be valuable for motor designers and engineers in understanding the impact of eccentricity and accordingly optimizing motor performance. Overall, the webinar presented a study that utilized simulation software to investigate and compare electromagnetic performance of a Nissan Leaf model with different eccentricity inputs, specifically analyzing torque, flux density under current excitation. Thank you so much for attending today's webinar. See you in the next webinar.